Okay. So, we are discussing about that LTI systems and their implementation. Now, come to the frequency domain representation of the discrete signals and LTI systems. Okay. So, what is there? Suppose I have an LTI system in here, okay, LTI system which is Hn, let us. Okay. Now, I want to provide a input and I get an output Yn. If I provide a input Xn. Okay. Now, I want to know frequency response of this Hn. Okay. So, mathematically I can do many things, but so what is Yn? Yn is nothing but a Hn convolved with x of n, which is nothing but a k equal to minus infinity to infinity hk into x of n minus k, okay, x of n minus k is okay or not. Okay. Now, let us consider I want to find out the frequency response. So, if I excited the systems with an individual frequency, each and every frequency, let us say 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz, 6 hertz, 7 hertz, and then I try to find out the output for 1 hertz, 2 hertz, 3 hertz, then I get the frequency response of the system. So, instead of xn, let us say input the single sinusoidal. So, it is e to the power j omega n, j omega n I can instead of. So, I apply a e to the power j omega n where omega is distinct, let us for 1 hertz, then I change the omega for 2 hertz, then I change the omega for 3 hertz. So, I can do that way, okay. And n is the number of samples. So, I apply a e to the power j omega n, what should be the output? Then Yn is nothing but a k equal to minus infinity to infinity hk, let us hk into x of n minus k is replaced by e to the power j omega. So, e to the power j omega n minus k. Okay. So, which is nothing but a k equal to minus infinity to infinity hk e to the power minus j omega k into e to the power j omega n. Okay or not? So, if I write down e to the power j omega n is nothing but a k equal to, because this is not depend on the k. So, e to the power j omega n outside minus infinity to infinity, I can write down hk into e to the power minus j omega k. Okay. So, what is e to the power minus j omega k? What is e to the power hk? So, I can say the Yn is nothing but a e to the power j omega n at where k equal to minus infinity to infinity hk into e to the power minus j omega k. So, this term is nothing but a frequency response of the systems, frequency response of the systems. So, I can write down this term as a e to the power j omega n h of capital H frequency plane e to the power j omega, frequency response of that LTI system. So, if you see e to the power j omega is the frequency response of the said LTI systems. Okay. Now, I can say if I see this equation, if you see this equation, what is there? This is a complex number. So, that has a magnitude and there has a phase. So, I can say h e to the power j omega has an complex. So, it has an phase, or you can say the magnitude, which is nothing but a h e to the power j omega mod, and e to the power j phi omega is the phase. So, I can say h is a real part and imaginary part. Again, this is a complex number property. So, cos omega j sin omega k. So, I can write real part is nothing but a cos part and imaginary part is nothing but a sin part minus h k sin omega k. So, magnitude response is nothing but a complex number, real square plus imaginary square. Phase is nothing but a tan inverse or arc tan inverse imaginary by real part, and group delay function is nothing but a tau omega is equal to d phi omega by d omega. Okay. Those things will be used frequently in signal processing of speech signal processing. Okay. Then I am not going this property, you can find out the phase component is nothing but a odd function and magnitude response is nothing but a even function. Okay. So, this is the LTI systems signals which the DSP concept will be used later on. There is another important DSP concept is there, that is will be used, I am not explaining this curve, that is called discrete Fourier transform. I think many of you know that one is called discrete time Fourier transform DTFT, discrete time Fourier transform, another is called DFT, discrete Fourier transform. Here the time domain signal is discrete, but frequency domain it is continuous. Time domain signal is discrete, but frequency domain it is continuous. So, discrete time Fourier transform, time domain it is discrete, but here discrete Fourier transform, input is discrete and frequency domain also it is represented as a discrete. Okay. So, this is a DTFT and DFT. Okay. So, DFT xn is in DTFT xn is digital, but whatever I get x omega is continuous. But here xn is also digital and x omega is also digital. Okay. Sometimes we write it x k discrete frequency instead of omega. Okay. So, what is the concept behind this? I am not going this one, this DFT I am describing the DFT. So, what I will do discrete Fourier transform. So, discrete time, first you just know the equation of discrete time Fourier transform. So, I can say x of omega where the frequency is continuous is nothing but a n equal to minus infinity to infinity x n e to the power minus j omega n. Okay. Now, I said that frequency domain it also discrete, that is called DFT, discrete time and discrete Fourier transform. So, it is not discrete time Fourier transform, it is discrete Fourier transform. So, this omega is replaced by k, k is the discrete Fourier transform. So, n equal to then becomes 0 to n minus 1 x of n e to the power j omega n k. Why it is you say it is minus infinity to plus infinity, it is 0 to n minus 1, why? I said discrete frequency, the frequency axis also discrete, and if I say that the frequency, that means I am sampling the frequency scale also. So, suppose I have a frequency range this one, here to here is f, I want to discretize it. Okay. So, I am saying let us divide this length with a n number of discrete value. Okay. So, I divided this n number of discrete value. If it is n number of finite length discrete value, I can say then it is the period is after n, I am saying the signal is repeating itself. So, x k is a period of n, capital N. The number of sample I have taken, I have the number of discrete sample, the discrete sample I have made the frequency response. So, this is if you explain it like this way. So, this is if you see this is continuous frequency, I discretized it with a number of discrete value. Okay. So, if it is discrete DFT, then equation is x k is equal to n equal to 0 to n minus 1 x n e to the power j omega n k. Okay. So, if it is that, then this n is called DFT, length of the DFT, length of the DFT. Now, suppose I have a signal whose sampling frequency Fs is 8 kilohertz. Sampling frequency is 8 kilohertz. Okay. Now, I said I take n is equal to let us 1000. 1000. I divided whole frequency range is the 8 kilohertz. 8 kilohertz frequency range. I divided in 1000 number of pieces, equal amount of pieces. So, I can say each pieces. So, k is varies from 0 to 1000, 0, 1, 2, 3, 4, 6, 4, 5, 6, 8 up to 1000. So, I can say that whole 8 kilohertz space is divided in 1000 pieces. That means, every sample k value k equal to 0, k equal to 1 means it is separated by 800 hertz. So, the value distance between the two k value is 8 hertz. This is called frequency resolution. So, frequency resolution is nothing but a Fs by n. So, suppose I want to find out the what is the frequency analog frequency value at k equal to 10. So, it is nothing but a into k is equal to f. So, at k equal to 10, in this case Fs is 8 kilohertz, 8 into 1000 divided by 1000 into 10. So, 80 hertz. So, if my signal is contained 80 hertz component, then the power at here will be come here. Okay. So, once I want to draw draw a DFT, suppose I done a DFT. So, I can say DFT, once I done the DFT, I have a xk. Okay. So, xk is nothing but a n equal to 0 to n minus 1, where n is the DFT length, x of n input signal e to the power minus j omega n k. Okay. Now, xk is a complex signal, sk is a complex signal. So, a complex signal has an amplitude and has an phase. Okay. So, I can write this signal is nothing but a cos and sine a plus jb. Okay. A plus jb. So, if it is a plus jb, then I can say xk has a magnitude response, which is defined like so. Discrete signal is third bracket, always represented by a third bracket. Slide maybe it is first bracket, but discrete signal is always represented by third bracket. So, mod of xk is nothing but a root over of a square plus b square, that is called magnitude response. So, what is the phase response? Theta is nothing but a arg of theta, arg of xk, theta is nothing but a tan inverse b by a. Okay. Now, suppose I told you I have a signal xn, find out the magnitude frequency response, frequency magnitude response. So, find out the magnitude frequency response of x. So, I have to plot the mod of xk. So, after computing DFT, I get a plus jb form. So, I compute the a square plus b square root over, that is the amplitude. If it is voltage, then it is it has to be square to make it power. If it is power, then it is root over of a square plus b square. So, now if I want to draw it, this axis is k and this axis is the power mod of x k. So, k is nothing but a k is varies from 0 to n minus 1. Now, I told you, okay, I do not want the discrete frequency k. Can you make it with the axis of f? Instead of k, can I replace this axis by f? Very easy, because f is equal to nothing but a, if this signal is sampled, this x n is sampled is 8 kilohertz and my n is equal to 1000, then I can say 8 k divided by 1000 into k, I get the corresponding frequency. So, instead of 0, I can mark 0, this will be let us frequency f 1, f 2, f 3, f 4 for different k value, I get the analog frequency value. Okay. Now, if you see here f is equal to 0. So, x 0 is nothing but a frequency is equal to 0, that is nothing but a DC component of the signal. So, x 0 is the DC component of the signal. So, those property you have to know, frequency resolution, DC component, how do you make the k to f conversion, those things will be used in implementation of digital speech processing. Okay. Now, there is another property, I am not describing this one again. So, the symmetry property is there. So, if I say DFT is called symmetry, after DFT xk is symmetry, sk is obey the symmetry property. Okay. That means, if I draw it here xk, let us this is my k axis k. So, at here n minus 1, it is nothing but a fs. At k equal to n minus 1 is nothing but a fs. Okay. So, if fs by 2 is my signal limitation. So, I can say it repeat the property, this is the fs by 2 point or n by 2 point. So, 0 to n by 2 minus 1 give me the same, this information and this information will be same information for baseband signal. So, after analyze the frequency, if I use 1000 point DFT, 500 point property will be repeated in here in mirror in nature, symmetric like. So, I can take this one only to find out the frequency response of the signal. Okay. Then DFT magnitude, when a real input signal contains a sine wave component, a peak amplitude a 0, the integer number of cycle n, then cycle over n input sample, then it is nothing but a mr equal to a 0 into. So, amplitude of the signal will be magnified by n by 2 if it is real valued signal. If it is a complex signal, it will be n number of. So, when you do the inverse DFT, I should normalize the amplitude by if it is real input signal. So, it is n by 2, if it is a complex input signal, then it will be n. Okay. And there is a DFT leakage, all those things you can find in that DSP book. DSP leakage means there is two kind of things if you see. Suppose I have sampled a signal in 8 kilohertz and of a signal, let us the signal has 50 hertz. So, 50 hertz signal, sinusoidal signal has sampled at 8 kilohertz. Okay. So, if I take the 1000 n equal to 1000 sample, then the frequency resolution is 8 hertz. So, for every k I will get 0, then 8 hertz, then 16 hertz, then 24 hertz, then let us dot, then 48 hertz and then next one is 56 hertz. So, my resolution does not support the 50 hertz. So, the power, but the signal has only power at 50 hertz. So, if I make the DFT, so instead of looking like 50 hertz single spike, it will look like this. Power will be distributed at just an computation point. So, this will look like this. So, this is the DSP computational leakage. Okay. Then there will be another effect, windowing effect also will become. I will discuss later on when we design the filter. Okay. Now, you know that implementation of DFT, discrete Fourier transform, is done based on fast Fourier transform algorithm. So, FFT is not the transform, FFT is an algorithm to implement DFT. So, that is why it is called fast Fourier transform algorithm, fast Fourier transform, FFT. Okay. So, FFT is an implementation procedure for DFT. So, if I say the DFT is nothing but a x of k is nothing but a sum of n equal to 0 to n minus 1 x of n into e to the power minus j omega n k. So, how many number of complex multiplication is in here? N cross n, n cross n complex multiplication is there. Now, I want to reduce it. I want to reduce this complex multiplication so that it can compute very faster. So, how can I do it? That is why it is called fast Fourier transform. So, instead of n cross n, can I use some other method which can computationally reduce, which can reduce the computational cost of the DFT? One method is called fast Fourier transform. I will discuss only radix 2 algorithm, other you can study from the DSP book. So, radix, I just discussed the philosophy, and this radix 2 algorithm is most commonly used algorithm. So, if I say I want to reduce the n cross n, I ask you from the computer science background that suppose I have a search space. If I make it binary search, then it is log 2 n. So, that means if I instead of computing using the whole signal, if I disseminate the, or if I somewhere I can disseminating the signal in some you can small chunk, and then if I compute, is it help us? Yes. So, what they done FFT radix 2 algorithm, that if I take the length of the DFT is, we can say that if the n can be represented by 2 to the power something, the length of the DST restriction is that I want to divide the whole signal in binary space, in two spaces, 2 part, then 4 part, 5 part, like that. It's like the binary search, whole number divided middle, first part, second part, and then I will do the first part, then I will do the second part, like that way I want to do it. So, what I want, that length of the DST must be expressed by this way, 2 to the power something. So, I cannot take n equal to 1000, because it cannot be expressed in 2 to the power something way. So, if I take n is equal to 1024, then I can say okay, it is nothing but a 2 to the power 10. So, this is the restriction radix 2 algorithm, that is why it is called radix 2 algorithm. Then whole signal xn either can be broken in time domain, or I can use whole xn and broke the computational output basically which frequency domain output in small number of chunk. So, either xn can be divide, or I can divide xk also. 2 space I can divide the signal. So, let us start with the disseminating time algorithm. So, here what I do, instead of computing whole DFT at a time, I divide the input signal in 2 terms, one is even term, another is odd term. Then again this one is divided even and odd, and even and odd, until unless I reach 2 point, where I cannot divide, one even and one odd. Okay. So, this algorithm is described in a book, you can do that. I just explain you by a, let us take the 8 point DFT, 8 point DFT, n equal to 8. So, that means it can be expressed 2 to the power 3. So, 3 stage I can divide it. So, first stage, let us the signal is x 0, x 1, x 2, x 3, x 4, x5, x6, x7 and x7. So, 8 number of signal I have taken, n equal to 8. I divide this signal space in two space, one is odd and even. Okay. Let us even. So, 0, 2, 4, 6, 1, 3, 5, 7. So, I can say let us start the signal, instead of taking the signal 1, 2, 3, 6. So, I take the upper part, let us 0, 2, 4, 6 and then I take 1, 3, 5, 7. Then again this can be divided into two part, even 0, 4 and odd 2, 6. Again it is even 1, 5, odd 3, 5. So, once I get two signal, I compute the DFT. This is called butterfly algorithm. I have not details discussed the mathematics of butterfly algorithm. Okay. Now, if you see, I get the output x0, x1, x2, x3, x4, x5, x6, x7. Now, you may say, how do I divide the signal in odd and even if it is my signal size is 1024? Okay. There is a trick, if you know that just that trick I will discuss, that is called bit reversible, the technique. If you see 8 n equal to 8, then 0 0 0 my represent 0, 0 0 1 represent 1, 0 1 0 2, 0 1 1 3, 1 0 0 4, 1 0 1 5, 1 1 0 6, 1 1 1 7. So, 2 to the power 8 n equal to 8, I require 3 bit, this 2 to the power 3 bit I require. So, I can see the 3 bit I can generate 7 number. Now, to do this odd and even distribution, what I do that access the signal in bit reversible format. When you access the signal, the index term reverse the bit. If it is 10 bit, reverse the bit. So, what I will do? I reverse the bit. So, instead of 0 0 0, I write 0 0 0 because reversible and non-reversible same. 0 0 1, I write 1 0 0. 0 1 0, I write 0 1 0 same. 0 1 1, 1 1 0, 1 0 0, 0 0 1, 1 0 1, 1 0 1, 1 1 0, 0 0 0 1 1, 1 1 1, 1 1 1. If you see 0 4 2 6 1 5 3 and sorry 1 5 3 7. So, this arrangement is done automatically if I just access the signal, the index of the signal is changed in bit reversible mode. So, if it is n equal to let us 1024. So, I require a 10 bit to represent the index. When I access the signal, I will change the bit reverse, I get it and then I do the calculation whatever is required for butterfly algorithm. So, that I have explained in DFT. I am not explaining details because this can be explained details in DSP class, you know it. Now, I come to the application side. So, once I done the where I use the DFT or frequency transform in speech, if you see, suppose I have a time domain signal, I already showed you time domain signal and this is this portion I have selected, this portion of the signal I have selected and take the frequency response of the signal. Okay. Now, there is a point, if I take n is equal to 1024 point 1024, that means order of the DFT is 1024. So, I take the signal 1024 sample signal Okay. So, if I suppose I have a long signal which is stationary signal. So, whether I take this portion or I take this portion or I take this portion, this portion, this portion or this portion, the signal property is remain same. In that case, I do not have any problem. Now, suppose the signal time is also changing, along the time signal property is changing. So, if I say, if I take this portion of the signal 1024, so whatever the frequency response I will get, that is the average frequency response of whole signal, means I am considering during this time the signal does not change its property. So, what I am losing? I am losing the time domain resolution of the signal. Time domain resolution I am losing. Okay. Now, if I want to increase the time domain resolution, what I will do, instead of n equal to 1024, let us I take n is equal to 256. Then my time domain resolution is increases, because my window size, the size is very less. So, I can get the better time resolution. Now, what is happened? Since f is equal to frequency resolution is nothing but a fs by n, if n is decreasing, the frequency resolution is also decreasing. So, once I increase the time domain resolution, my frequency domain resolution is decreasing. So, if I take long signal, time domain resolution is losing. If I take small signal, frequency resolution is losing. So, this is the limitation of Fourier transform. That is why people are use more number of other number of transform like wavelet, EMD, all kind of things is used. Okay. So, let us forget about that things. Suppose I told you record a voice, or I can say record a signal and design an algorithm or design and compute or draw its frequency response or spectrum of the signal. I am not saying spectrogram. So, amplitude response representation is called spectrum. So, what is that? It is nothing but a mod of xk versus frequency. That drawing is called spectrum of the signal. So, if I told you record the vowel a and take the n equal to 1024 point and draw the spectrum of the vowel a. So, I will draw the frequency response of the vowel a. That means, if I can draw it with respect to k and I can convert the k with respect to f, then I get the frequency response of the signal. Okay. So, this can be drawn in linear view or log view. Log view means, if you see there is a two kind of view, log view and windowing I will come later on. So, log view and linear view. Okay. So, there will be a log view, I can take the output as a log. So, log spectrum or normal spectrum, this is the normal spectrum. Okay. So, then once I get the spectrum, I get the form and frequency plot. So, that means I know the form and frequency representation of the signal. All details I will come STFT when we discuss. Okay. Now, this is called spectrum. Now, when you draw this kind of representation, this is called spectrogram. So, difference is that spectrum is frequency versus power, means the power of each frequency plot. Spectrogram, x axis is the time, y axis is the frequency and power is converted into the intensity or color. So, it is a 3D curve. So, the representation is that if you see there is a long line, same line is coming. Why this line is coming? So, what I do? So, I want this axis is time, this axis is frequency and intensity as an amplitude. So, I have a long signal. So, I take the small chunk of the signal from here and find out this point, then I plot it here. So, for this whole chunk frequency representation will be same. Next chunk I will take and then I plot it here. So, if it is 10 millisecond window, then this 10 millisecond will be same, this 10 millisecond will be same. That is why you see this kind of things are coming. Okay. So, this is called spectrogram and earlier one is called spectrum. Okay. So, next is the digital filter. This is the last portion of the DSP review. So, digital filter. If you say any forget about the filter, any transfer function, let us I have a transfer function, let us Hz, Z transform you know. Hz is nothing but a y output yz divided by input xz, it is capital X capital Y. Okay. Yz by xz is the transfer function Hz. So, this Hz is nothing but a some polynomial function. So, let us it is Pz by Qz is nothing but a polynomial function. So, solution of Pz provide me with the 0 position and solution of Qz provide me the pole position. That is why Hz is a pole 0 filter, pole and 0 filter. That is why Hz has a formant and 0 provide the antiformant or resonance, anti-resonance. Okay. So, pole 0 filter. Any filter can be implemented using a pole 0 function. So, I can implement Pz and I can implement Qz and I can implement Hz. Okay. Now, how it is look like this? If you see the mathematics, so there is a number of pole, m number of 0, if it is order is m number of 0 and n number of pole. Okay. So, every pole and 0 has a complex conjugate. So, that I will discuss later on that every pole has a complex conjugate, if it is complex pole complex 0. So, it is if the real value Hz is real, then every pole on every 0 complex pole has its conjugate value. So, if there is a pole in here, there will be a conjugate value pole in here. So, this is the unit circle. If all poles are lie inside the unit circle, then we can say there is a causal and stable filter. Okay. Now, how do we implement filter in digital domain? Okay. So, I can say Hz has an impulse response, Hz has an impulse response, or I can say Hz in time domain it is nothing but a Hn. So, Hn has an impulse response, it can be finite or it can be infinite non-finite. So, if I say if it is infinite, so it can be finite or infinite. So, if I say that it has a finite impulse response, then we said the implementation is called FIR filter, finite impulse response filter. If I implement using infinite impulse response, n varies from minus m to plus infinity, then I call IIR filter, infinite impulse response filter. Okay. So, one is finite impulse response, another implementation procedure is infinite impulse response. Okay. So, let us discuss about the FIR filter, which is called finite impulse response filter. Okay. Now, what do you mean by a filter? That is very important. What do you mean by a filter? So, suppose filter means something is unwanted, I want to discard, that is filter. Now, in a signal, suppose I have a signal which has a frequency response, let us all frequency are present. Now, I want to cut down after 5 kilohertz, I want signal or system should not produce, let us signal should not produce any response. That means that filter is that filter frequency response is that up to 500 kilohertz or 500 hertz, I want response should be like this, and after 500 hertz I do not want anything. So, that means 0 to 500 hertz all frequency components should pass to the output, and after 500 hertz none of the components should pass to the output. Then it is called low pass filter, because low frequency component is pass, high frequency component is attenuated to 0. Okay. So, there may be, I may want this type, that okay, frequency component between 500 hertz to 1.5 kilohertz may pass, this portion also becomes 0 and this portion also becomes 0. So, that is my requirement, or I may say this is called band pass filter, or I may say I want a filter after 1.5 kilohertz all frequencies should pass, below 1.5 kilohertz none of the frequencies should be there. So, that should be 0, that is called high pass filter. So, it is low pass filter, it is band pass filter, it is high pass filter. That is my ideal filter frequency response I want. Okay? This is the ideal response, but if I implement it with a finite impulse response filter, then I, instead of getting that single, that this pass band with 1, instead of this, if you see this is flat 1, here I can get a some kind of variation, that is called pass band ripple, or instead of sharp cutoff I can get a transit point, that is called transitory response, and after that instead of 0 I can get some signal here also, that is called stop band ripple, pass band ripple, stop band ripple and filter transition bandwidth. So, where the amplitude is 1 to 0 is transitory. So, that transitory portion, that frequency range is called transition bandwidth. So, you can say normalized is then the peak ripple pass band, peak ripple in stop band and normalized transition bandwidth. So, this point to this point is called normalized transition bandwidth. So, this is pass band frequency, this is the stop band frequency where I want to stop the filter. So, this bandwidth is called transition bandwidth. Okay. So, how to implement the filter? FIROA, two methods. So, I can say that I have a filter whose response is Hn. If I know the transfer function, time domain transfer function of the filter, then I convolve the input signal, I get the output of the filter. Or what I can do, I can take the frequency response of the filter which is Hk, and I can take the frequency response of the input signal Xk and multiply Hk into Xk, I get Yk. Then I take the IDFT to get the Yn. So, either I can implement in frequency domain, I can frequency domain transfer the Hk, then I can get take the time domain signal in frequency domain, multiply both and get the output, and take the IDFT, get the input. So, this is the two implementations, either frequency domain implementation or time domain implementation. Okay. So, have you understand? Either I can implement the filter in time domain or I can implement the filter in frequency domain. Okay. Now, suppose I want to implement the filter in time domain or frequency or any domain when I want to implement, how do I implement it? FIR filter implementation. So, suppose I have a long signal is there, is a long signal. If I want take the whole signal, so signal may be huge signal. So, I do not want to take the whole signal at a time. Then what I have to do, I have to cut the signal this portion and apply the filter here. Then take the next chunk, I can do that way. Once I cut the filter, what I am doing? Whether I take the DFT or filter, once I cut the signal in a chunk, that means if this is Xn, I am multiplying Xn with a window function which is 1 within the interval, let us it is L minus 1, 0 to L minus 1. So, 0 to L minus 1 window function is a square, amplitude is 1, after that its amplitude is 0, that is window function. So, if it is 1, if it is this type of window, I am not multiplying the signal with any function, this is called rectangular window. Okay. Now, once I do the rectangular window, then my frequency response of the output frequency yn, if I take the yk is also contain the frequency response of this window function. So, I am not getting the exact frequency response, only the filter and input signal, but also it is combined with window function frequency response. That is why I will get the different kinds of ripple. So, if you see, different kind of window function are defined to reduce the different ripple, stop band ripple and pass band ripple, and different kind of window function is defined. That is called Blackman window, Hamming window, Henning window, Kaiser window. So, everybody has a window function that is multiply with the input signal and then convolve with the filter transfer function, I get the output. So, if I implement the filter, so this is the common Windows frequency response. If it is frequency response of the rectangular window, if you see like this, so ripple is much more. If I want to butter Blackman window, frequency response is like the Hamming window, this Henning window, this. So, most cases Henning window we are using because the ripple is very less. So, different window function has different kind of frequency response. This frequency response will be combined with the frequency response of the signal and passed through the filter. Okay. So, it is time domain multiplication, that means window multiply with the signal in time domain. So, frequency domain it will be convolution. So, xk will be convolved with window function and then multiply with frequency response of the filter. Okay. So, this is happening. Details I will discuss when I discuss about the STFT, short term frequency response, short term Fourier transform. Okay. Now, if you see the example implementation for a time domain signal, suppose I want to design a low pass filter, cutoff frequency is omega c. So, this is the frequency response of the filter. So, user in implementation of filter, user will provide the frequency response of the filter. I have to design if I want to design in time domain, then I have to derive the time domain representation or time domain transfer function or time domain impulse response of the filter and then convolve with the input signal. So, if I do that, I will get this kind of response and then I can implement it in time domain. So, if you see the book, there is a different, so different window has different type of transition bandwidth and peak side lobe. So, this is the ripple in peak side lobe and this is the transition bandwidth. So, if I rectangular filter, if the order of the filter is m, then transition bandwidth delta is nothing but a 4 pi by m. Okay. So, m is the order of the filter. If I implement the filter in FIR way, so I said finite impulse response. Ideally, and filter has an infinite impulse. So, I truncated the infinite impulse to a finite number. If it is m, then m is called order of the filter. Ideally, if I want to design a low pass filter, this is infinite impulse response. Once I truncated it, I cannot get this half cut off. So, I get a transition. So, this transition bandwidth depends on the what kind of window I have used to truncate the filter transfer function or truncate the signal. Okay. So, if I use the rectangular window, then it is 4 pi by m. If it is Hamming window, 8 pi, Hamming window 8 pi by m, Henning window 8 pi by m. Okay. So, depending on the requirement, I should use which kind of window I should apply. Next one, how do I implement a band pass filter? So, suppose I implement a low pass filter up to 500 kilohertz, it is 500 hertz. So, bandwidth is 500 hertz. Now, I want to implement a band pass filter of 500 hertz bandwidth with the frequency between the 1.5 kilohertz to 2 kilohertz. So, what I will do? I will just shift this low pass filter to 1.5 kilohertz frequency, so that I get this one. Understand or not? So, it is nothing but a frequency shifting of the low pass filter. So, any band pass filter I can just implement the low pass filter of the desired bandwidth and shifted that frequency response where you want to implement the band pass filter. Similarly, suppose I want to design a high pass filter of 1.5 kilohertz. Okay. If the sampling frequency of the signal is 8 kilohertz, then in frequency scale, what is the maximum signal? Up to 8 kilohertz I can get. Baseband signal is 4 kilohertz again, even I can get the baseband signal is 4 kilohertz. So, it is nothing but a band pass filter 1.5 kilohertz to 4 kilohertz. So, I designed that filter and shifted at 1.5 kilohertz, I get the high pass filter. So, that way I can design the filter. Details filter design I am not going here, because that you can that is prerequisite of this course, that if you want to know the digital filter design, digital signal processing you have to study. I just give you some concept of the, or you can say that this is overview of DSP. So, how to implement an IIR filter? There is a lot of methodology are there. Bilinear, I can take that derive that filter transfer function in S domain, then go to the bilinear transformation to make it Z domain, and once I get the Z domain transfer function, I can use a discrete system to design that transfer function. Okay. So, that way we can implement. So, this is the prerequisite part which I will be referred many times during the speech processing class. So, this is the overview of DSP. Please go through these slides. If it is there is a, suppose you do not cover the DSP, then if you do not want to understand a particular point, then you read that DSP book, Proakis, Menalokis or whatever the digital signal processing book you can read, and also you can post that I am not understand this portion, then I will help whatever way I can do, because if I just consider the DSP, then I am not able to complete the speech part. So, I am just truncated that I just or summarize the DSP required DSP things in here, and some DSP also I require higher end DSP signal processing algorithm I will be used, and that time I will describe that things when I will use them. Okay? So, thank you.